In this relatively brief video, we're going to talk about something that's actually very important. It's something that I know that you've all seen before. Maybe you know the details of this, but what we're looking at is actually called a uh, topographic map, or sometimes called a contour. So, what you see on the right is obviously, a hill, a mountain, maybe a small mountain. But on the left is kind of a two-dimensional mathematical abstraction of this thing that you see on the right. So beautiful natural scenery here. Obviously, this is a three-dimensional object. We can see it, we can tell that this is three-dimensional. But over here we essentially have something that's flat. It's like a piece of paper, and people have drawn a whole bunch of curves on it. Now, what are these curves? Well, let me take one that's clearly visible. So let's look at this one right here that's labeled 11,000. If we kind of follow it around, you think of this as a trail that might be kind of carved out in this mountain. And if you stay on this trail, and I am going to assume that this number here represents an elevation. Maybe it's feet above sea level or something like that. So if you stay along this particular trail and you walk along this mountain, you're always going to be at a constant 1,100 feet above sea level. If you decide to go rogue, let's say you're a part of a group of hikers, and you decide, what, I'm gonna go rogue and I'm gonna try to get up to the top of this mountain faster, and you start jumping from one of these curves to another curve to another curve, then based on the labeling on this topographic map, your elevation would be increasing, right? And notice how as the elevation increases, so as you go in this particular direction, the curves get smaller, and that's because you're approaching the peak of the mountain. So these down here, like again, the one for 1,100 feet, these are really kind of spread out. They're not so nice and compact, and that's because, again, this is towards the base where you have a lot of land, to along which you can hike. But as you go up the mountain, the elevation increases, then the contours essentially get smaller and smaller and smaller, right? Now, depending on what it is you're trying to depict, right, these curves that we see here, right, could represent different things. Again, I'm just assuming that it's elevation. I look at a mountain, I see numbers going up. I figured, well, yeah, you're going up the mountain, your elevation increases. But maps like this could be used to represent lots of other things. It could be used to represent temperature. Sometimes you'll see these on what they call the curves in that case would be called isotherms. So again, temperature is not realistic given the numbers here, but let's say this was, 110 degrees or something. Then what it means is the temperature along this curve, that same one, would be a constant, 110 degrees. And then going up, it would increase, which again isn't practical. Usually you go up and your temperature um, decreases. But the whole idea of these types of maps is that they're very, very useful because they allow you, right, to represent something that's three-dimensional, essentially on a two-dimensional surface, right? So it's like you lose, obviously, looking at this wonderful natural scene here, you lose some details, right, going to a weird looking map like this. But depending on what sort of information you want to retain, then this would be a perfect rendering of what you see here, right? So we're just going to briefly talk about what the mathematics of level curves and contours what does it do, or how does it relate to these functions of several variables, right? And we're going to focus on functions of two variables. So let z equals f of xy define some surface, right? And remember, previously we looked at different plots. All right, we use that fancy software to render several surfaces. So let's say we have the equation of one of those surfaces, and let's say it is in the explicit form. So we're going to assume that the z is our dependent variable, and then the x and the y, they represent a pair of independent variables. So again, going back to this context here, if again we think of like our z-axis going like, emanating right through the middle of that mountain pointing upwards, then we can think of z as like the height above the sea level, right? And then the x and y would then represent the point that we are somewhere on the ground, right? And as we move along that ground, so as we change the x and y, look at what's going to happen with the z. It's going to change as well. So that's why we can interpret this as being dependent on these two. So let's say we have the equation in that form. If the equation of the surface, so if this surface is sliced, so how are we going to slice a surface, is sliced by the plane, a really simple plane, z equals k, right? So suppose now, so ground level, let's assume that ground level is z equals 0. Then z equals k would just be, you would be a certain number of feet, or whatever your measure of distance would be, above sea level. And then it's like you'd be cutting across the mountain parallel to the ground, right? And then what would happen is when you slice the mountain and then you look at the cross section, you would see one of these curves. So again, the idea of fixing your height, which would be in this case fixing your elevation, and walking around, you're going to trace out a particular curve, and that particular curve is what we define as, so let's write this, right? So then all the points, oh, let's write that properly. So okay, let me get this off. I'll scroll down. I think if we need the image, we can scroll back up. So if then all the points on the intersection, so on the intersection of z equals k and z equals f of xy, all those points, right? Again, those are the ones that make all these different curves at a fixed level are called, right? So okay, let's see. So these points of intersections, so all of them together are called, actually, no, let me not say it like that. So all the points of intersection, they form what is called a level curve of height k. So height K, right? And then a set of level curves, right? And what that means is at different heights, so at different heights, so that set of level curves, so let me underline that. When you have a bunch of them like we see in our topographic map, that set is called a contour map, or just a contour. So a contour of the surface, so of f of xy, right? So let me go back up. So we just defined a level curve is a specific height. So again, at least we can still see a portion of it here. So you're at a fixed height, let's say of this 11,000 feet. And somehow this is the curve that is traced out along this mountain at that elevation. But then, right beside it, you have another one. Now, they're not all labeled, right? Imagine if they were all labeled, the map would just look really messy. So you have a lot of them that are just kind of isolated. But it's when you look at all of them collectively now, like all of these here, these are all different level curves, but they all make up a single thing that we call a contour, right? Contour plot or contour map or simply contour. All right, so let's look at an example. So what type of question might you have? So let's just do a couple here. So examples. So again, let's start with the simplest of surfaces. We're just going to take a plane. So and I'll write it in the explicit form. So I will isolate the z. So let's say the equation of the plane is this: negative x plus y plus 1. That's equal to our z, right? And so again, remember, it could also be given like this: f of x, y is equal to negative x plus y plus 1, right? Sketch the level curves of this surface. So the level curves of this surface, or we could say this plane, once we recognize that it is the equation of a plane, just in the explicit form, for levels. Let's take k equals negative 1, k equals 0, and let's take k equals 2. So if for instance, we're thinking that k equals 0, like I said, that might be sea level, some base level, then this would be 1 unit down, right, from that base, and then this would be 2 units above that base. So for each of these levels, we're going to have a different equation. So let's find the equations first and then plot them all together to come up with our contour, right? So it's not going to look as detailed as the one above, but it will be in the same spirit. So let's say this: so when k is equal to negative 1, then that means our z value, right? So the height is negative 1. So we're going to replace the z with the negative 1. That's what this is saying here, right? So your z is now a fixed value, and we want to see what kind of equation in terms of x and y is left. So if I put a negative 1 there, then I have this. So if I look carefully, so if I were to solve this for y, because now that z has a fixed value, this is just an equation that involves x and y. So we can actually plot this equation in our xy plane. And that's the whole idea of going from something that's three-dimensional, fix your dependent variable, and then suddenly you get something two-dimensional. So it's often referred to as like a projection of the level curve of this surface onto the xy plane. Sounds more complicated than it is. But anyway, if we were to rearrange this equation, we would get that y is equal to x minus 2, right? Basically, I subtracted 1 from both sides. I added x to both sides, isolated the y, and I got this. Well, why am I isolating the y? Because of all the types of equations that we know how to solve, ones of the form y equals f of x is certainly the predominant type, right? So, and let's repeat this process for the other two values of k, and then we will go ahead and plot each of the equations that we obtain. So let's see what's the level curve when k is equal to 0. Well, at this height, essentially we're at sea level, so our z is at 0, and we would have negative x plus y plus 1. Doing the same trick, what do we end up with now? Y is equal to x minus 1. And if you notice, my elevation, if you will, went up by 1 unit. And look at this constant here went up by 1 unit. Now that's because this equation is pretty simple. So we're working with something that's relatively simple, so it'll be easy to go ahead and sketch these curves once we have them all, right? And so when k is equal to 2, fix our z value at 2, and then we end up having same expression, x plus y plus 1, and then again, same thing, add x, subtract 1, and then we're going to end up having that y is equal to x plus 1. Now, each of these equations, so let me circle them. They're simple enough that we can express these also in explicit form. And these are all linear equations. These equations all represent lines. And what's interesting about these lines is that they're all parallel because they have slope 1, but the y-intercept is all different. So let's sketch each of them, and I'll just do, let's do this on an xy plane. So yeah, let's just go ahead and put some markers on our axes. Probably don't need too many of them. I chose the numbers so that it wouldn't be too difficult, right? So let's start with the first one, when k is equal to negative 1. It could also be written as z is equal to negative 1. It doesn't have to be k, but as long as you're clear what fixed value of your dependent variable you're working with, then you can derive the level curves. So this one will have a y-intercept of negative 2, and then slope 1, so you just go up 1 over 1. So in fact, yeah, let me do each of these in different colors. So this one, right, is when k or z is equal to negative 1. And let's look at, so this one now, the y-intercept is negative 1. So basically just shift this one up 1 unit. So it's going to be here and then here. So yeah, like I said, they're going to be parallel. I'm pretty sure my sketches are not going to be perfectly parallel, but you get the idea. So like that. And then let's sketch the other one. So x plus 1, so now start up here and then up and over, right? Again, we're going up 1 over 1 because that's our slope, right? Rise over run in this case is 1 over 1. So then we end up getting, let's see here, let me just kind of extend this. Oh, not perfect, but you get the idea. So these are the two three level curves that make up this. So this single plot is a contour plot of this surface, right? And again, we ended up with relatively simple equations because we started with a pretty simple surface. Here's one that's a little bit more interesting. So let's try something like this. So for this surface, f of xy, let's make it x squared plus y squared, like that. What is the level curve? So what is the level curve for, and then like I was saying, you could see it's, you could have it stated something like this, where instead of using the letter K, we could use the letter Z, and let's say for Z0 equals 1, Z0 equals 4, Z0 equals 9. So again, 3 different levels, right? So here there's not going to be much to do. So let's see. So at Z0 equals 1, then again we would interpret this as our Z variable, like, so even though it's not written there explicitly, we would assume that Z is a function of X and Y. So then what this means is 1 is equal to X squared plus Y. Well, this is your unit circle, right? So this level curve would be a circle. And then the rest of them would also be circles, but just with different radii. So you'd have 4 is equal to x squared plus y squared. And then at z0 equals 9, you'd have 9 equals x squared plus y squared. So these are all circles centered at the origin. This one, so let's say it like this. So these level curves are circles centered at the origin, looking at our standard equation. And remember, the square root of the number that's on the right hand, or on this side of the equation, is going to give you your radius, right? So these are all centered at the origin. And then I'll just say this one is with radius 1. Square root of 1 is 1. But then this one is with radius square. Let me write it so you see exactly the operation that I'm performing. The square root of 4. And then this one is with radius root 9, which is equal to 3. So over here, like when we did the level curves for a plane, that's what we started with. We ended up with a bunch of parallel lines. Now, when we do the level curves for, now this one is that kind of surface is essentially, it's a parabola in 3D, right? So instead of just having like an x squared, you have an x plus y squared. So it's what we call a paraboloid. It's like a 3D parabola, right? And so, yep, we only need these because our radius doesn't get any bigger than 3. So again, let's start with this one. So this one is in blue. There is our nice unit circle. And then let's say this one is in green. So again, just kind of move out 1 unit in all 4 directions. And then this one has radius 3. So there is our 3rd level curve, and that would be the contour. So these now, and these are described, these are what we would say are concentric circles. They have the same center, but, different radii. So concentric circles. So what happens is the more, not really complicated, but or I guess we could use the word complicated. The more complicated our surface is, the more intricate the level curves are. And that's why, so now, like, going back up to where we started, just imagine what the equations would have to look like to generate these types of curves, right? These types of curves. In fact, a lot of those implicit equations from your first semester of calculus, many of those implicit curves, when you plot them, they do end up looking like this, right? So you go from, simple lines to simple circles, and then you end up with some fantastical other curves. But it all starts from the idea of here's a surface. How could we even think about representing something 3D in a 2D representation? Well, try to fix one of your variables. And it makes sense to fix your dependent variable and then let your independent variables vary. And this is what we end up with, right? So that's the concept of level curves and contours. And I hope you'll think about it, and the next time you look at you watch the weather report and you look at the map, it's like, oh yeah, look at those lines, and a lot of those lines represent temperature or might be rainfall or something like that, along which some constant phenomena occurs. So there's math everywhere. You just have to look hard enough. And if you're not sure, I'll point you in the direction to look. Just ask. See you then.